Right, so this is the third video looking at reversible reactions in industrial processes, and the first two looked at the Haber process, and this one is going to look at the contact process. So I'm going to fast forward now. Here we have it. Right, so the contact process occurs over 4 steps to make H2SO4, sulfuric acid. So in the first step, you take sulfur. I love the colour of sulfur, a bright, vibrant yellow solid, and you roast it, react it with oxygen effectively, and form sulfur dioxide, which is the oxide of a non-metal. So unsurprisingly, that is an acidic gas. You then take your sulfur dioxide and you heat it again with oxygen. Okay, now this is the key step in the reaction. This is our reversible reaction, hence when we study the contact process at school, we always study it alongside other reversible reactions, and you need to know the conditions that are used in that reaction, or that step of the reaction. So we use 450 degrees C, we use 2 atmospheres of pressure, and we use a catalyst of vanadium pentoxide, and we will discuss why we use those conditions a little bit later in the video. The sulfur trioxide, which is formed, is then dissolved in sulfuric acid, which is a slightly bizarre step, or at least my students find it slightly bizarre, and that forms a substance called oleum, H2S2O7. And the oleum is then dissolved in water or mixed with water, and that forms the sulfuric acid. So what my students usually say is, hang on, we've made SO3 at this point, why not take sulfur trioxide, mix it straight into water, dissolve it in water, and then, well, you put those two things together, you get H2SO4. Surely, doing it in one step is a much better way of doing this. Why bother doing it in 2 steps? Unfortunately, doing it in 1 step is dangerous. This reaction is extremely exothermic. A huge amount of heat is given off. And if you're going to do this on a very small scale, that's fine. But doing it on a very large scale, there'd be huge amounts of heat generated, and you'd be getting horrible, horrible fumes given off. And as I said before, you're dealing with oxides of non-metals here. You'll be getting really acidic fumes given off, and that's not particularly pleasant, as a mild understatement. It's also dangerous. So we have to use these 2 steps, and even though you have to put a little bit of sulfuric acid in here, you get 2 molecules of sulfuric acid out, so you kind of double your money. And then my students usually ask, well, hang on, where do we get this H2SO4 from in the first place then? And the answer is, well, we have to do this reaction on a very small scale to give us some H2SO4, which allows us then to bulk up the process. Now, I'm afraid these steps do need to be learnt for the exam. And now I'm going to look at why we choose those conditions. So I'm just going to make a few additions to this slide. I'm just going to say that the reaction has an enthalpy change which is negative, and I'll write down the conditions here, and we will justify them in the same way that we justified the conditions we used in the Haber process. So I'm going to address temperature first of all, and to do that I need to use this key bit of information here. Delta H is negative, and what that is telling us is that the forwards reaction is exothermic. That means the backwards reaction is endothermic. So an increase in temperature shifts the reaction in the endothermic direction. So very much like in the Haber process, high temperatures give low yields. So why on earth do we choose a temperature of 450 degrees C? Well, it's to ensure that the reaction is sufficiently quick, okay, that it has sufficient pace, that it's fast, it produces the SO3 at a fast enough rate. Okay, a lower temperature, higher yield, but let's change that, but too slow. A higher temperature would be fast but low yield, because the equilibrium is shifted in the endothermic direction, in other words over to the left. So we have to use a compromise temperature. Now, why do we use 2 atmospheres pressure? In other words, double atmospheric pressure. Well, increasing the pressure in a reversible reaction shifts the equilibrium position towards the side of the reaction with fewer gaseous molecules. And in this reaction, we have 2 gaseous molecules on the right and 3 on the left. So a high pressure, or a higher pressure than that, would give a high yield. But it would be dangerous. Increasing the pressure of a system is always dangerous. So therefore, why do we not use a lower pressure? Well, if I lower the pressure, this would shift the equilibrium in the direction of more gaseous molecules, in other words, to the left. So a lower pressure has a lower yield, but cheaper and less dangerous. So we use, again, a compromise pressure. We're compromising between cost, danger, and yield of sulfur trioxide. So we use something in the middle. Okay, we don't use a sky-high pressure, nor do we not use atmospheric pressure. And why do we use a catalyst? Well, the catalyst increases the rate, but it's worth noting it has no effect on the yield. Now, what do we use sulfuric acid for? And when I ask a class this, they generally give me some nice answers about, we use sulfuric acid to do some nice reactions in the lab. It reacts very nicely with magnesium ribbon, producing magnesium sulfate and hydrogen. And that's true, but it's not really an industrial use of sulfuric acid. And the IGCSE specification suggests 3 uses for sulfuric acid. It's used to make paint, it's used to make detergents, and it's used to make fertilizer. The acid itself isn't a fertilizer, the acid itself isn't a detergent, it's not a paint either, but it's used to make these 3 things. In fact, it's often combined with ammonia to make ammonium sulfate, which would be a reasonable fertilizer. I think it's also worth thinking about the properties of sulfuric acid. And one interesting use of concentrated sulfuric acid is that it's a dehydrating agent. Conc H2SO4, dehydrating. And there's some fantastic reactions you can do with concentrated sulfuric acid. You could add concentrated sulfuric acid to blue hydrated copper sulfate, and the conc sulfuric acid would turn it white. It would shift, well, it would turn. I'm going to run out of space doing this, I can see that. but you've got conch sulfuric there, plus 5H2O, and it would release the water. So you'd go from having this blue solid here to forming a white solid here. You could also, and I'm just going to see if that works, yeah, I think I've just about successfully moved that. You could also add it to sugar, sucrose, and if you do that, you get a spectacular reaction happening, and you remove H2O from the sucrose and you're just left with carbon. So we have 11 waters and you're left with 12 carbons, and it's absolutely fantastic. You can find videos of this on YouTube. Type in sugar and concentrated sulfuric acid and you see the white powder, I've pressed the wrong button here, the white sugar rapidly forms the black carbon powder, and you can sort of see almost this black carbon monster rising up from a beaker of sugar, which is spectacular. Now that concludes our look at the production of sulfuric acid, and indeed a look at the reversible reactions which are used in industrial processes.